Okay, let's dive in. Think about this. You've got a drone, right? And you need it to fly over some really tricky ground.
Uh-huh.
Like maybe a farm field that's all hills, or I don't know, a construction site with lots of bumps and dips.
Right. Not just a flat parking lot.
Exactly. And the job is precise. Maybe it's spraying crops evenly or getting super detailed photos for an inspection. You need total coverage.
Yeah. Covering every single spot is critical.
But it's not just about coverage, is it? It's also about doing it smart, efficiently. Because the ground isn't flat, the drone's constantly going up and down.
And that constant change in elevation, that's really the core of the problem, isn't it?
It seems like it.
I mean, a simple back and forth pattern like you'd use on flat ground just
Yeah.
won't work well. The slope changes everything.
How so?
Well, it affects how high the drone needs to fly to keep the spray or the camera view consistent. It affects the energy it uses fighting gravity going uphill.
Ah, okay. And how it needs to move to compensate.
Precisely.
Okay, and this is where it gets interesting. We've been looking at some source material that shows how, well, high-level math comes into play.
Yeah, the kind of math you might actually be studying right now if you're in college.
Exactly. Stuff like calculus. And it's being used to solve this very real, very modern problem of optimizing these drone flights.
And what really stood out in the sources we looked at was the direct use of differentiation and integration.
Right. Not just theory.
No, not at all. These are the actual tools engineers are using. They build mathematical models of that bumpy terrain and then use calculus to figure out the absolute best path for the drone.
So the goal of this deep dive really is to understand how these concepts, specifically derivatives, help optimize drone spraying paths. And the sources emphasize it's about considering both the slope of the land and the total area you need to cover.
hmm The sources explain that the derivative basically gives you the gradient of the terrain.
Gradient meaning slope.
Yeah, think of it as the steepness and the direction of that steepness at any given point on the field, instantly. They might use techniques like partial derivatives, if you're dealing with a full 3D surface, to map out how that elevation changes as the drone moves.
So you get this dynamic map of the slope.
Exactly. And that rate of change, the slope that directly tells you about the drone's energy use
Yeah.
and what adjustments it needs to make for, say, effective spraying.
So it's way beyond just drawing lines on a flat map. They're taking real terrain data, maybe from LiDAR scans or something,
Could be, yeah. Or photogrammetry.
and building a mathematical model of the actual ground, bumps and all, and then applying calculus to that model to plan the flight.
Right. And the sources talk about incorporating that slope information into what they call a cost function.
A cost function, so not just about distance.
No, it's more complex. The cost includes things like the extra battery power needed to climb a steep hill, or maybe the need to slow down on a descent to keep the spray density right.
That makes sense. You're optimizing for energy or time, not just the shortest path on a flat plane.
Precisely.
Hmm.
And then integration steps in.
Okay, how does that fit?
Well, integration helps you figure out the total effect over the entire field. Think about calculating the total energy used or the total amount sprayed, especially if the field has weird, irregular borders or obstacles you have to fly around.
Ah, so you're adding up all the little costs along the path?
Essentially, yes. You integrate that cost function, or maybe a coverage function, over the whole complex shape of the field. The goal is to find the path that minimizes the total integrated cost, like minimum energy for full coverage.
Wow. So understanding derivatives, how things change point by point, and integrals, how to sum those changes up, it's exactly what's needed for this kind of real-world problem, flying efficiently over bumpy ground.
It really is.
Yeah.
And the sources we read actually gave examples. They showed paths calculated using this calculus method were significantly better saving energy, cutting flight times compared to simpler paths that ignored the terrain.
That's a clear practical benefit.
Definitely. And it makes you think. The sources show calculus works great for optimizing based on slope and area. Those are big factors.
So what else?
Well, given that derivatives help us handle these changing variables, what other complex factors in drone flight could calculus help with? Things that also change constantly.
Like maybe real-time wind shifts,
Hmm.
or the drone getting lighter as it sprays its payload.
Exactly.
Yeah.
Or even avoiding obstacles that pop up unexpectedly.
Mm.
Could calculus help model and optimize for those dynamic elements too?
That's a fascinating question to chew on. Definitely something to think about next time you see a drone buzzing overhead and wonder what math is guiding its journey.